Hello and welcome to the York Consortium for Conservation and Craftsmanship, to this, the first of our autumn series of Second Tuesday talks. I'm Bethan Griffiths and I'm your host for tonight. I'm a consortium committee member and others may know me through my work at the Ironwork Studio as an ironwork designer and conservation consultant. These Second Tuesday talks, first started in summer 2020, have gained a wide audience from across the UK and indeed the world. We are again delighted to have you with us. We also again welcome new non-members, so I hope that regular participants will forgive me for saying a few words to introduce the consortium. The consortium was established in recognition of York's central role as a hub for heritage conservation and craft skills. Over the last 20 years, we have built upon this to emphasise the close integration between craftspeople and conservators. We provide a point of focus for both practitioners and those generally interested in supporting our heritage. In addition, the Foundation's annual bursary scheme has also flourished, having awarded over 250 bursaries to date to support the development of craft and conservation skills. Before we hear the presentation, a little bit more housekeeping. We are not anticipating any technical issues, but if we do, please do bear with us. There will be a question and answer session at the end of the talk. Please submit any questions via the Q&A icon. If you can't see it, hover your cursor around the bottom of the screen and it should pop up. You can submit questions at any time during the presentation, but we will only be answering them at the end during the Q&A session. We anticipate a finish time of 8:15. But if there are outstanding questions by then, for those who want to stay with us, we will continue answering for a few more extra minutes. And so now for tonight's talk, the structure and properties of wood as a living material. And I'm delighted, in fact, to welcome our speaker, Roland Ennos. So he'll be joining us soon. Hello there, Roland. Still muted, but I'm sure we'll get that sorted in a minute.
I'm here.
You are here. That's good. Excellent. Technology is working at last. So for those who don't know Roland, he is visiting professor of biological sciences at the University of Hull. He has spent his career researching and teaching the engineering of plants and animals, from insect wings and birds' feathers to human fingerprints and fingernails. Most recently, Ronald has concentrated on the largest organisms on Earth, trees. He has investigated how their roots anchor them into the ground, how their leaves provide air conditioning for cities, how the trees branch, and how their wood skeletons transport water to their leaves and resist the huge forces applied to them by gravity and wind. Roland's summarised what we know about the biology and ecology of trees and forests in his book Trees, published by the Natural History Museum. He has also become interested in our crucial relationship with wood, a relationship which started even before our ancestors came down from the treetops and continues to this present day. He has reinterpreted the human story from this wood-centred point of view in his recent book, The Wood Age. This shows our evolution, how the development of civilizations, and even how the course of modern history have all been shaped by our relationship with this most versatile material. And now for the talk. Roland, over to you.
Thank you very much. And thank you very much, Bethan, for your lovely introduction. And good evening, everyone. I must say I feel a bit of a fraud talking to so many people, so many experts and craftspeople, because my woodworking skills sadly were very limited. My woodworking career rather short and not very good. I never did manage to do very good mortise and tenon joints. So I did, as a teenager, I'm pleased to say I've made some very good, I thought, cages to house my stick insects. And I used to make balsa wood models. Nevertheless, I think as someone who has studied, as Bethan mentioned, the relationship between biology and physics and engineering, the biology and engineering of plants, I might have something to say, a different perspective to help to at least to give you on the subject of wood and how to use it. And so tonight I would like to talk to you about, as the title says, the structure and properties of wood as a living material. Now, one of the first things to say is that trees are just like other plants. The only difference there is that they're much larger. So they so they have to use wood as their skeleton. And what we need to know to understand trees and wood is we need to know how they grow their skeletons, how they transport water to their leaves through those woody skeletons, how those woody skeletons help them to stand up. And knowing this will help us understand the structure and properties of wood a lot better, I think. And hopefully it should also help us understand how it can be shaped and used, and give some perspective for the craftsman on those sorts of subjects. First of all, I'd like to just introduce the structure of trees, which should be well known to everybody. And the first thing to say is that wood is laid down, as you know, in a ring. It's laid down in a ring around the outside of a tree's skeleton, and they grow in length at the same time. So as a result of that, trees are structured really rather like Russian dolls. The oldest and narrowest rings are in the center and at the base of the tree, and as the tree grows, each new ring gets longer and it gets thicker. So the rings give the visible grain of the wood and show its history. So if you want to know what a tree was like at the start, one way of finding out is to look right back into the center of the first growth ring. And that's something that has been explored, of course, by the sculptor Giuseppe Pannoni. And I went to the Yorkshire Sculpture Park in 2018, I think, and had some fantastic sort of cross sections of trees and things. And he was showing something about the history of trees from looking at their skeletons. Now, let's have a look at what wood is actually composed of. And the first thing to say is that wood, like all biological structures, is made up of cells. And so here's our tree trunk. This is a scanning electron micrograph of wood. And the first thing to say is that the cells are long and thin, and most of them are arranged longitudinally. So they're going up and down the tree trunk. This is a cross section through the tree. Most of the cells are fairly circular. The rings show the different ages of the tree. There's just one different sort of important different sort of cells in the tree, and those are the ray cells. And the ray cells go from the center radially out to the outside. We'll talk about their importance later on. You can see them here at the bottom, if you can see my little arrow, and you can see the cross section of vesseled wider cells interspersed with thinner, thicker walled cells. Next thing to know is to say, well, why is wood arranged like that? And one of the reasons is because of the hydraulics of wood. Now, a tree, being a plant, has to draw water up to its leaves to supply for photosynthesis. How does it do that? Well, just like all other plants, the water is in fact raised by the power not of the tree pumping water up, but of the sun dragging water up. The sun evaporates water from the leaves, which is then drawn up from the roots under tension. It's being sucked up from above. So this water is actually stretched and that's quite a strong force. And you'll notice immediately that one of the big advantages of wood being made of long tubular hollow cells is that those are actually ideal to pipe water up to the leaves. And the tree does that all for free because the sun provides the energy. There's just one downside to this arrangement, and that is because the water is under tension, it's quite easy for those water columns to break. The cells soon get blocked by air bubbles. It doesn't happen immediately. There's two main causes for the cells being blocked and for the water column to break. Firstly, in drought, like in our summer we've just had in Britain, but more importantly, in frost, because if a tree freezes, the water inside freezes, and when it melts again, and the tree tries to draw water up to its leaves again, air bubbles immediately come in. The water conduction is lost. So it's only the outer part of a tree which actually is able to draw water up to the top, and that's the bit of the wood that's known as sapwood. It's this bit around the outside, both in a hardwood and in a softwood. What does a tree do with all that dead, all the stuff which isn't any good? Well, what it does, it will still be useful to help it stand up. So what it does is the tree then pumps resins and gums into the center, into the wood. That helps to prevent decay, stops nasty fungi from getting in and rotting the wood, makes the wood darker as a result. So you can say the difference between the heartwood here, which is just used to support the tree, and the sapwood, which still has a hydraulic function. In the softwoods, the conduction tends to last longer because most of the cells are very long and thin, so it's more difficult for bubbles to form, and so the heartwood is only starting to form in the center of this larch here. So that's the cause. That's why there are differences between the different parts of trees, with the white sapwood and the dark heartwood. What about the next thing that the tree has to do is to stand up. And in order to understand why having long cells going longitudinally is good, you have to understand what happens when the wind starts to blow a tree sideways, or when gravity starts to pull a branch downwards. If the wind's blowing sideways here, for instance, that actually puts the trunk into bending, and that sets up forces which are actually aligned along the direction of the trunk. On the windward side, you get tensile forces set up that tends to stretch the wood on that side, and on the leeward side, you get compression forces. The wood tends to be crushed. So all of those forces that are set up are actually aligned parallel to the trunk, and so having cells longitudinally arranged is absolutely ideal for a tree. So not only is it good for piping water up to the top, but it's also good to withstand the forces it has to cope with. So that's why most of the cells of a tree in wood are aligned parallel to the trunk or to the branch. But as I mentioned before, there are these cells. These are arranged radially. We can just see them going in that direction here, for instance, and they're arranged in sort of columns. If a tree didn't have rays, the outside would continually break off, like the bark of a birch tree, for instance. And so these rays are ideally suited to pin the growth rings together. And it's a very clever arrangement of cells. That's the main trunk. Things get more tricky to a tree when it starts to branch, because if all the cells went across either that side or that side, it would be very easy to split the tree down the center. Branches would just break off easily. So what actually happens, and what a very clever PhD student of mine found, was that at the center of branch junctions, the grain actually wraps around to form a sort of clip arrangement. And in big trees, you even get big rings of bark all going round. That forms a lovely, strong attachment mechanism to hold the branches together. So the arrangement of cells in wood is a brilliant arrangement to make them as strong as possible. But not only are the cells well arranged, the cell walls, which make up the cells, are also very well designed. If you look at the cell wall structure of wood, you'll see that it's actually a composite material, rather like fiberglass or carbon fiber. In those composites, you have a stiff fiber, quite large ones, in a matrix of plastic. In wood cells, the fibers are tiny. They're microfibrils of cellulose, which is one of the strongest and stiffest materials in nature. They're sort of like huge long crystals, and they're embedded in a matrix of smaller molecules, hemicelluloses as they're known, in between, and also lignin, which joins up and helps to sort of join those side to side. Lignin doesn't actually stiffen a tree, it just strengthens the link between the fibers. It's a very clever arrangement. Cellulose fibers are about sort of 20 times stiffer than steel, so when they're properly arranged in the wood, weight for weight, wood cell wall material is as strong as steel, but it's nowhere near as tough. Steel is particularly useful because it's incredibly tough. But wood has an answer to that too, and that's because of the arrangement of the fibers within the cell wall. This is a close-up of a cell. There's several layers. I mean, all these things in biology are complex, but all we need to know is that it's mostly made up of this middle layer, S2 layer, and in that layer, most of the fibers are arranged at 20 degrees to the long axis of the cell. They coil upwards. It's a good at being stiff because they basically help to resist tension very well. But a big advantage of them coiling is that when you break and you pull apart some wood, when the wood's broken, the cell walls, when you're stretching their cell walls up and down, the cell wall buckles and those fibers unwind rather like springs. And then all the different fibers pull out, and that makes massive degree of disruption, takes huge amounts of energy, and leaves a very rough fracture surface. So that's why if you break wood, snap wood with your hands, the fracture surface is very rough, makes the whole thing extremely tough. So across the grain, if you try to break the wood across the grain, it's as tough weight for weight as steel. So wood is a fantastic material for being tough, but it's not the same in all directions. It's very brittle along the grain because when you're pulling the wood apart from side to side there, there's no toughening mechanism, which is why wood is so brittle along the grain, why it's so it splits so easily, which is a big problem. So wood is a fantastic material designed brilliantly for trees, helps them to be fantastic structures. Now, when it comes to wood, though, and our use of wood, there's just one fortuitous fact, nothing to do with wood being good for trees. It's just lucky for us. And that one fortuitous fact is that as wood dries out after you cut a tree down, the wood will dry out. Moisture content drops from about 25%, usually to around 10 or 12%. As that happens, the wood biological materials, as they dry out, get all brittle. But that's not true of wood. It actually gets stiffer and stronger as it dries out. These are the strengths, how the strength increases. Not a brilliant graph, but you can see that as it, both the stiffness and the strength increase as the wood gets drier. So fortunately for us, it becomes a better material. The only downside as wood dries out is because it's stiffer and stronger, it's harder to work. And there's a second thing, as it shrinks, that wood also, and the water evaporates from the wood, it dries and it shrinks, especially from side to side and especially in the tangential direction. And we'll see that can be quite a problem later on in the talk. But all these things affect how we can, the different ways in which wood can be worked. And I like to start with perhaps the most unusual way that wood is worked, and that's usually was invented not by us, but by our ancestors, the great apes. Now, one of the things that happens in a living tree is if you bend a branch, it doesn't break all the way across. It starts to break, but then as the fracture surface reaches the center, what happens is it becomes easier for the branch to split in between the rays along its length, and you get something called green stick fracture. And this is a twig of an ash tree which has been broken in that way. And once you've split it in half, it's much easier to bend, and you can start to weave it. And that's exactly what orangutans do when they build their nests. They build nests every day. Chimpanzees do that, as do gorillas. They are probably, our great ape ancestors were probably the world's first carpenters. They build a nest, they sit on a thick branch, and then they lean over, find other branches, thinner branches, and they half break them using green stick fracture, bend them towards themselves, and then weave them into a nest. They can break off even thinner branches, as this one's doing here, and turning it into the pillows and mattresses. And then this is the final nest arrangement, which has been built into a nicely woven nest. It's something actually we also do, and that's done not by modern carpenters, but by country craftsmen. For instance, people when they're laying hedges, they do the same thing, half break their trunks of their little treelets they're using to make the hedge, and they bend them. And it's also used by people using small poles to make hurdles. They can half break them and then weave them and to make hurdles. So that's a very rough and ready way of making sort of weaving wood and turning it into useful structures. But there's a second way, and which has proved much more useful for people, and that's by shaping wood by breaking it and splitting it when it's still green. We saw earlier that it's much easier to break wood along its grain than across the grain, and that was certainly something that our ancestors found when they had to try and use stone tools to make their buildings and do their woodwork. This is a 6,000-year-old axe from the Isle of Lewis, the Schuler-Shader axe. It's got a lovely carved, polished stone blade, but that's really very thick, not very good at cutting sideways across a tree. The other main tool that the Neolithic people used were adzes, which were like axes, but had their blade at right angles. And you'll notice here that these adzes, they're made up from whole branch junctions from trees. So they're making use of the fact that trees are nice and strong, have nice strong joints to make an adze. And if you will try to cut a tree down using either of these, you have to do it at an angle. You have to cut the deeper and deeper sort of glancing blows until you get a sort of pencil shaped piece, and then you can eventually chop that tree down. It's not very effective at all, but once you've done that, once you've got a log, for instance, you can wedge it open by applying hammering wedges in at the end, and wood splits down the center very easily. You can then split it again and again, and you can actually make planks of wood using that process. And you could also, once you've cut a tree down, a lot of broadleaf trees spring up and produce lots of new wood, and you can use turning into what's known as coppice. Coppicing started probably about 8,000 years ago, and then you can use the thin poles, which are much easier to use, much easier to cut across, and you can use that that wood as well. And surprisingly, considering what rubbish tools early people had, they could do surprisingly fantastic things with it. So, for instance, the Neolithic people built the first houses of multiple occupation, which look really rather similar to our own. They have lots of beams, circular beams to hold up the roof along the ridge pole there. They can use planks to hold the sides of the building, or they could make hurdles, and they can use hurdles woven small bits of wood to make the doors. And that's a perfectly good, very nice, very large house. They even did the first, what we might recognize as proper carpentry. And notice that and this is some Neolithic well lining, which was found in excavated in Germany. You need a well line. If you dig a well, you need something to line it so the mud doesn't all come in and it closes up again. And you notice this is really cleverly designed. At the bottom frame is actually made with mortise and tenon joints, the sorts of joints that I'm used to be rubbish at making as a woodworker as a teenager. There's the mortise and tenon elements, and the ones higher up, they use sort of overlapping joints, crisscrossing each other. You might ask, well, how on earth do they do these cuts across the wood if they only had stone tools? Well, probably they used bone chisels. They got a long bone of an animal here, and if you sharpen that end, a bone is a lot tougher, and so you can turn that into or you could use a tooth of a beaver, which is also something that people did in those days, and you can actually start to make reasonable joints, still rather rough and ready. And you'll notice at the top, on the right hand side of the top part, the ends have been sort of hacked off. They weren't really very good at cutting sideways across wood. Fortunately, things got rather better about sort of between 4 and 3,000 years of BC, with the advent of bronze as a new material. Being a metal, bronze is not only stiff, but it's also much tougher and strong, and so you can make it into much narrower blades. So the Bronze Age people made equivalents of stone axe, a bronze axe, much thinner, much sharper. The same with the adze. They made chisels, very fine chisels, and then you could hammer that in to cut sideways through wood. They could use long, thin draw knives to flake off wood and shape it more cleverly. And they could even made simple saws. So that made it possible to do a lot more precise woodworking. That enabled construction buildings with not just round poles, but squared off beams, like this medieval tithe barn from near Heathrow Airport, for instance. And then you could cut off and hew it flat and make a nice, much more neat structure, removing all the sapwood, just leaving the heartwood, which lasts much longer. So we can make better building, the people can make better buildings, but with much better, precise woodworking, they could also make, for the first time, make proper wheels. This is the earliest wheel known to have existed. This is the Ljubljana wheel from which comes from Slovenia. It's made up of two planks of ash wood, and those have had rebates cut in them across the sides, and then had battens put in between and doweling. So it forms a single large wheel, which all these people could then use to pull chariots, and then later on they could make wheels with spokes. But a great advantage in the old world was that people managed to make wheels, and because of the precise woodworking, they could also build plank ships sink. It could have, had good enough joints to be watertight. This is the earliest one known. It's in fantastic condition because it was actually never launched. This is Khufu's ship, which was found from beneath the pyramids, or one of the great pyramids. It was reconstructed. It was meant to carry the pharaoh across the night sky, so it's really a symbolic boat, but it's very similar to the ones that the Egyptians would have used. And good plank boats were also common in Britain in the Bronze Age. Some of the best ones were found in actually North Ferriby in East Yorkshire in the 40s by two school children, and in the British Museum now. So and there's a nice, if you go to Brig on the other side of the estuary in the Discovery Centre, there's even a lovely raft which they made of planks from about 1500 BC. And of course, the great advantage of having big plank boats is that means you could cross seas, and that eventually enabled people to have trade empires across the Mediterranean, and eventually for Europeans to cross the Atlantic and conquer the New World. For instance, that's the reconstruction of the Santa Maria, which is the ship of Columbus. But a real big advance was made in the Iron Age, with iron's a much stronger material even than bronze, and so you can make a whole new set of tools which are much even better at cutting through wood much more precisely. You could, for the first time, have a rip saw, this is a medieval version, designed to cut longitudinally through wood to make nice, straight, perfect planks. And you could then have a crosscut saw to cut across the wood to help to make all your joints. And there was even an improvement in tools to smooth the wood, to make it smoother. And those that, for instance, in planes where you have like a draw knife, but the tool is actually mounted on a proper framework, so it's much more accurate. And because people had these new tools, they could at last make they could cut and make carpentry out of seasoned wood, which has the big advantage is that it's already been seasoned before you cut it. It means that it's not going to change shape when you're using it, and it won't finally split. So it's made a big advantage. Help people to make lots of square furniture, right-angled joints, but iron also allowed people to make other ways of developing curves. And it was soon after iron was first came out that people first started using lathes, where sort of rods of wood, where branches of wood could be mounted and spun rapidly around, and you'd have a material hard enough to cut into it to form the beautiful legs of chairs, for instance. And it was at this stage that people also started to steam bend wood so you can make curves in the wood. And so, for instance, you can make a beautiful, precise carpentry like this Windsor chair from the 18th century. So by this stage, ever since the Iron Age, people have been able to do extremely good carpentry. But one of the things is not all woods are equal. You wouldn't be able to make this chair and it be any good if it's made out of balsa wood, for instance. Not all woods are equal. And you might well ask, well, why aren't all woods the same? And the answer is there's all sorts of reasons why wood can differ. One reason is that they ancestry. The conifers were the first trees to go on our planet. They only have thin tracheids, which have to do the job both of piping the water and being strong. So, and if you look at a cross section through conifer wood, you'll notice that it's only got thin tracheids, tiny rays, and the whole structure is pretty homogeneous. That's in contrast to a broadleaf tree where there are special mechanical cells called fibers, and then special broad cells called vessels, which are used to do the water transport. And to stick that together, they have to have larger rays to stop the whole thing from falling apart. So they're quite there, so that makes a difference. But a more important difference comes with the ecology of the tree, because not all trees are the same. Most trees, and this is all of these trees are broadleaf trees. Most trees are diffuse, have a wood anatomy which is known as diffuse porous. For instance, beech, teak, mahogany. The cells are arranged more or less the large cells are arranged more or less homogeneously around the tree. They're small, they can cope with cold weather, or they don't need to bother about coping with cold weather. If teak and mahogany, they only grow in hot weather. So lots of trees, tropical trees, have got this sort of arrangement. But two important trees for people in the temperate areas are ash and oak, and they have quite a different structure of their wood. The wood is known as ring porous, and at the start of every year they lay down huge vessels for water transport, and then later in the year they lay down the mechanical vessels. Why do they do that? Well, both of these trees, most of their relatives are from more hot climates. The ash tree, for instance, is related to olive trees, and the oak tree, there are loads of tropical oak trees. I've been in the rainforest of Borneo and acorns have fallen on my head. So both of these trees are only just getting used to growing in cold weather, and what they do to cope with the cold weather, with frost, is that they just give up every year. All of their vessels get clogged and blocked. And so at the start of every year, they have to lay down a new layer of big, large, open vessels in order to allow water to climb up to the top of their trunk. But the delay of that is the reason why ash and oak are the last two trees to come into leaf in spring. And there's other problems with other aspects. Because that produces a line of weakness, they have to have large rays going right from the center to the outside, and oak in particular has gigantic rays. You can see them. That's why oak is highly figured and makes it also not homogeneous at all. So those are different. There's another difference, and that trees differ because of the survival strategy that they adopt. Some trees try and grow as fast as possible, as quickly as possible, to get it into a gap in a forest or by the river. They're known as pioneer trees. Things like poplars, willows, and balsam, they're very fast growing, but short-lived. And to grow fast, to grow a thick trunk as quickly as possible, they make lightweight wood. They don't bother putting many defense chemicals in their wood. It's pale, and basically their wood's no good for carpentry. So poplar is mostly used for like making matches or to make pallets, for instance. You wouldn't use it for carpentry. Balsa only used for sort of models and things. Whereas if you have a long-lived tree, in order for the tree to survive, it has to make denser wood, put lots more defense chemicals into it, and long-lived trees are excellent for carpentry. So if you have a good wood, that's probably come from a long-lived tree, particularly ones from the understory of canopies, things like holly or ebony, which is a understory tree from the tropical rainforest. They're really excellent for carpentry, nice, really dense wood. And finally, wood differs with climate. In our temperate climate, there aren't that many. It's cold. Don't have such a problem with rot. So the wood tends to be paler, and if you make it, it's not very good. If it's kept out in the rain, it tends to rot quite quickly. And the tropical trees, on the other hand, having to deal with very nasty, large amounts of fungi in the warm, humid conditions, things like mahogany and teak, they have to put down make darker wood. And so teak, for instance, can cope with the rain. That's why garden furniture is made out of teak. It's not made out of poplar. So, and it's for that reason that different woods are useful for different purposes. And it's useful to have a look at contrast 3 different species. For instance, this is a violin. Violins tend to be made out of spruce. The reason being that the wood is made up of being conifer wood. There's no large vessel, so it's very good at conducting sound. It won't get stopped by lots of having huge layers of vessels within it. And the best violins, of course, are the Stradivarius, which were made from wood which is very slow growing from the Dolomites at a time when the Dolomites were very cold in the Little Ice Age, and the wood was very dense. So it meant that the sound can travel both upwards and sideways very rapidly, and that violin vibrates nicely. For woodwind instruments, the important thing is to get the sound traveling as fast as possible. So you want as dense a wood as possible, which is why many of the best woodwind instruments, like this recorder, are made out of ebony or blackwood, very dense, very bright tone, because the sound is the higher frequencies are magnified. And that contrasts with lime, for instance, a very soft, fairly soft wood, diffuse porous, so it doesn't have much pattern, very easy to carve, soft, and no figure to compromise it. And you can also contrast the different sorts of wood in their sorts of markets that they were suitable for. So oak, because it has those loads of big vessels in it, very big rays, it's very patterned but rather rough looking, and so it's never going to, in modern times, has never appealed to these sort of higher class markets, and it tends to be like for sort of farmhouse work, people tend to use oak, nothing sophisticated. And that compares with a sophisticated mahogany dresser here from probably one of the Adam from the Adam family, the mahogany being a tree which was harvested from the slopes of the hills in Jamaica. Beautiful dark wood, easy, nice to carve, and totally smooth. Not much figure to get it away. Just a small sort of lovely markings. So different woods suitable for different markets because the trees have different ecology and different ways of making a living. So it's worth thinking about when you've got a wood, thinking, well, what sort of tree is that from? How does that tree work? How does that tree survive? If you different trees live in different places, and it's quite interesting to see that. So I think that's all I've got to say really about all these different things. So in conclusion, the points I've made, firstly, is that wood is designed for trees, but the fact that it's designed for trees fortuitously makes it incredibly useful for us. Beautiful properties, especially along grain. But wood's cellular nature and the fact that most of the cells are longitudinal makes it a bit tricky to use. So you need to understand how those cells orientated and why they're orientated in the way they are. Third thing is that it's thanks to steel and the steel woodworking tools have made it much easier for us to precisely shape seasoned wood. We don't still have to shape wood when it's green and then have to cope with the changes that happen after it's been made. And finally, it's the contrasting ecology of trees suits their wood for different purposes. So I hope there's some pictures of my my books there, but I hope I've been able to say a few things at least that you didn't know that might find illuminating. Thank you very much.
Hello again.
Hello.
That was absolutely great. Thanks very much, Roland. That was really interesting. Certainly a deeper look at trees than I've ever thought I'd get involved with. But really, really nice. Well, you're so used to using wood, but you don't actually think of the material itself, do you?
Well, yeah, it's interesting because I always would, but it's quite interesting to see what different perspectives different people have on all these subjects.
Yes. Right, so we're now just about to go into the question and answer session. So just a reminder, if you want to put a question in and you haven't done already, please use the Q&A icon. And if you can't see it, hover your cursor around the bottom edge of the screen and it should pop up so you can put it in there. Okay, so, but we have our first question in, and this is, what happens in oak at the boundary between oak sapwood and oak heartwood that in just a year or so converts one of the least durable timbers into one of the most undurable, least durable to most durable?
Yes, it's an interesting thing is that you always think that wood is all the same, but of course, as the question shows, there's two different parts of the wood, and what happens in between the time when the wood is sapwood and when it's heartwood is that when it becomes heartwood, the tree's given it up as there being any use at all for conduction, and it's shut the whole part of that wood down. It's pumped chemicals into it, things like phenolics, tannins, resins, and gums, and that makes it that darkens it at the same time, but it's still it stiffens it a bit, makes it stronger in compression, but it also means that it's much more resistant to rot, as the question suggests. So it's all down to the survival strategy of the trees, from converting the wood from being a useful hydraulic material to being a material which is just used for mechanical purposes and which is designed to be as long lasting as possible to support the tree for maybe hundreds of years.
Yeah, several hundred years. Thank you. Last bit of this question was, why can't humans replicate this process?
Yeah, well, it's difficult because I don't know particularly how trees do that. They probably pump the water, pump the gums and things along the trunk or outwards from within. When you tannalize timber, that tends to be pressure treated from the outside, and then we pumping chemicals in from the outside. But for some reason, we just don't know how to be a tree so well as a tree does, and so it just doesn't manage to. We don't manage to pump the defense chemicals, and we don't pump such a range of defense chemicals in either. So and trees are actively evolving all the time. So new defense chemicals have different trees have different cocktails of defense chemicals. So what you want in a forest is a wide sort of different diversity of tree genomes. If all the trees are the same, then are the same gene, if they're all related, as elm was before Dutch elm disease hit, if they're all the same, they're easy for a disease to adapt to it, and that's why all our Dutch elm, all the elms died off in the 1960s. They were all just one. They were all just one clone, basically.
Oh, well, I'd have never thought that. Why that was. Okay, next question. Why does so much green timber split?
Oh, that's an interesting question. Now, what happens, as I was talking about, as wood dries, what happens is that it loses water, of course, and it tends to shrink. Now, it's difficult for wood to shrink along its length because there's so many fibers in that direction, and the microfibers, less so from side to side. It's much easier to shrink laterally, but in the radial direction, trees are reinforced also, of course, by the rays, and so wood tends to shrink much more in a sort of tangential direction. Which, if you have a disc of wood which you've cut off from a tree, a small thickness of branch, what will happen is the whole thing will open up and have a pie-shaped crack will open up into it, and it will split. That will split. That's also what happens in the timbers you get in an old cottage, for instance. They've all been carved when they've been green, and since then they've split. They've dried out and split, and you get those big long radial splits in the wood. It's not really a problem. It doesn't really weaken the wood or the beam materially, but it wouldn't look good if you made a table out of wood, green wood. And one of the big skills of people in sawmills and timber yards is the way they saw their wood and then dry it very slowly or very very controlled way in a drying kiln, so that the wood dries and yet it doesn't dry too much, so that it doesn't split.
Yeah, we certainly don't want split timber on our furniture, do we? Well, unless it's proper rusticated.
Well, the rusticated looks good, doesn't it? But
when it's in the right place.
Yeah.
Okay, so the green frame buildings are just as structurally strong with splits.
Yeah,
as otherwise it's just a visual thing.
It's a visual thing, and it just adds a bit of extra charm. And unfortunately, as I say, because of the stresses are all longitudinal, having those splits in that direction doesn't really weaken them. So that's quite fortunate.
Oh, very good. We have another question, and I hope I can pronounce all of this correctly. I heard that it's recently been suggested that the famous tone of the Stradivarius violins may be down to mycelium fungi in the wood, if I've got that right, if I pronounce that right.
Right.
Have you heard this, and do you believe it's true?
I hadn't heard that, to be honest. The story that tends to go around is that the tone of the violins is particularly good because in that period of time, 18th century, that Europe was still subject to the Little Ice Age, so that the trees in the Dolomites which they used were growing very slowly. They laid down denser wood as a consequence, which is what conifers do when they grow very slowly, and therefore that is that denseness of the wood that means that the sound travels so fast and gives them such a bright tone. I would have thought if they had mycelium, which are like which is the bits that hyphae that fungi use to feed, that would have started to tend to rot the wood and wouldn't do it much good. But I'd be very interested if you could pass on that sort of story and to find out more about it, because the relationship between trees and fungi is really rather fascinating.
Ah, so that's caught your attention, that one.
Caught my attention, yeah, very interesting.
Very good. Okay, we have another question in. Are there any apparent unprecedented diseases that are sweeping trees away in our countryside and forest?
Well, there are an awful lot of diseases, sadly, which are sweeping all sorts of trees around. We had a terrible one, of course, as I mentioned, back in the 1960s, where all our elms, big elms, died. Some elms still live, but when only small ones, and when they reach a certain size, they catch the disease again and die off. The really terrible disease at the moment is ash dieback, or cholera, which has just come in the last 10 years really, and is devastating the forest, the ash woods, for instance, in the Peak District, up in the Yorkshire Wolds and the Dales on the limestone where ash likes to live. And it's an interesting story about why that disease has arrived in Europe. And the big problem with tree diseases is foresters. And what forestry people always want to do is to bring in exotic species into a country and try to make them grow faster than the native species. I don't know why they want to do this. We have loads of, for instance, in Britain, we have loads of Sitka spruce trees, horrible things, which they've been brought in. And the story with the ash is that the cholera disease that kills European ash is actually a disease of Manchurian ash from Siberia. It doesn't kill Siberian ash, but Soviet foresters decided to plant Manchurian ash in Western Russia, therefore introducing the disease to places where the European ash lives, and then it's spread out from over there all the right of the way across Europe, and is killing all our tree, most of our ash trees. It's some of them might survive, but it's pretty devastating. Corsican ash brought into Scotland for some reason has brought a disease which is starting to kill Scots pines. Anywhere where people move trees has resulted in disaster. Japanese chestnuts were brought into America at the turn of the beginning of the 20th century, bringing a disease which has killed all of the great chestnuts of America. There's new diseases of cedar in Britain. There's all sorts of diseases. It's all because people move plants around, and in this case, it's all down to the sort of fashionable and what foresters like to do with trees. And I don't know why they want to do that.
So it doesn't sound like they're learning the lesson from this, if this has been going on for so long.
Not really. I have a brother who researches tree diseases, and he gets very angry. He does a lot of research on this and is trying to persuade people not to move trees around. But I don't know why foresters just seem to like to do it, and it's very difficult to stop them. Well,
it's got to be driven by commercial reasons.
Mm. Well,
so is that the same thing that affected Dutch elm disease? That was.
Well, I don't know if Dutch elm that was. I'm not quite sure how that got into Europe, but the big problem in England, as I say, was that all of our trees were just from one clone, and so once the disease got in, it spread very quickly and killed lots of trees very fast.
But the clone stuff isn't the same with the other.
That's not the same. No. So there is a chance. There is a chance that some of our ash trees, some of them are more resistant to the to the disease, and people are trying to breed from those and choose and plant some new, more resistant ash trees. So in the future we may get more ash trees, but if you go into, for instance, into the Peak District or the Wolds or anywhere, you see ash trees with the tips all dying off, and it's a very sad sight. There'll be an awful lot of ash for people to carve in the next few years, and of course that ash is a very good wood for burning, so there's going to be an awful lot of firewood from ash over the next few years.
Oh well, that's good to put it to some use. Yes. Okay, another question. Somebody is wondering what recent or any discovery excites you most.
The exciting discoveries are starting to be just how early people started to use wood as a material, because we talk about the Stone Age, the Bronze Age and the Iron Age, but people have been using wood for even before they started using stone. And one of the fantastic recent discoveries was of some wooden javelins that people found in Saxony in Germany. They were 350,000 years old, and yet they look just like modern Olympic javelins.
Oh,
so people were carving beautiful weapons and carving wood really well. And this was 350,000 years ago. It's before our species evolved. They were probably Neanderthal people or an even earlier species who are making wood. So the really exciting thing, I think, is that we're discovering that we are, as a species, we are a species which is adapted to working with wood and to living with wood, and that's something that we need to go back to for our sort of health and well-being. People always like working with wood. People love being around wood, living in wooden houses, and it's people and their engineers are starting to be able to make amazing wooden structures using new laminate woods, and it's great to see modern buildings that people actually like because they're made of a beautiful material with beautiful sort of arches and things. And if you like, for instance, in Sheffield, the Winter Gardens is a beautiful relatively new greenhouse made from parabolic larch timbers, large sort of laminated timbers, and it's just wonderful to see wood coming back into its own again.
Well, I certainly like seeing wood around us. Right, another question though. Where do you oh sorry, my thing's moved up. Where do you envision forestry going in the future?
Hopefully it will be going into a more sustainable future. That's already happening in places like Finland and Sweden, where people that have a much more wood-centered culture, and the big new thing is not to fell huge areas of wood and then replant. It's to cut individual trees down and gradually keep us some continuous cover forestry. Trees grow better when they grow in between other trees which are taller than them, because they grow straighter. The ecosystem isn't damaged so much, and it's altogether, and the soil isn't damaged as you don't massacre whole areas. And that's really the big new thing that I think we'll have to go with. In Britain, we're not used to it. We're not really a culture that has had much has been particularly interested in forestry. For hundreds of years, we bought most of our wood either from the Baltic states or increasingly from Canada and the United States, or from the tropics, from Jamaica, for instance. So hopefully we can learn from other countries and become more of a better forest culture. We've only got 10 to 12% tree cover here, compared with 30% in France, about 35% in Germany, and 70% in Finland. So we've got a long way to go to develop a proper tree culture.
But it must be so much easier to flatten the lot and take it out than it is to grow trees between trees and harvest it in that.
Well, yeah, that's true. That's what people have found, but it's
Still possible.
It's still possible, and if you get better quality straighter wood, which you do with these these more sophisticated techniques, then that wood is much more valuable than just having a load of sort of fairly quick growing trees that have grown in windy conditions. So there's a good deal of benefit and financial benefit even from growing trees in a rather better and more thoughtful way.
Oh, well put. Okay, another question. You mentioned different climates affecting the density of wood growing in those areas.
Yeah.
Is there any evidence of this affecting the sorts of wooden items people used and the woodworking techniques they used historically in different parts of the world? It's a long one.
Yeah, it is a long one. I think that it's difficult. I think that what you find is that in the tropics, most of our wood is quite similar. You get some lightish wood and some more dense wood, but you get much bigger differences in the tropics. So, for instance, wood can range from balsa, which is a density only about a tenth of that of water, to things like ebony and ironwood, which are heavier than water and which sink. So there's a bigger variety of things in the tropics, and you get an awful lot more, lots of fine carving of small knickknacks in tropical woods, ebony and things like that. And we tend to have a bit more rough and ready with our wood. The only exception being lime, which is so easy to carve and so soft that it's been carved into things by people like Grinling Gibbons into sheaves of corn and violin strings, and incredibly fine, but not strong enough to actually touch, as opposed to the tropical little statuettes with lovely hardwood, which are a lot more durable. So they're quite different cultures, really, and I think that the sorts of tree and wood does affect it, but in quite complex ways. Okay,
thank you. Next one. What makes a yew tree live so long?
Yew trees are they're conifers. They're very unusual. Most conifers, if you cut a conifer down, like a spruce tree or a Leylandii, it will die. Yew is one of the only conifers that will actually resprout from the bottom, like an oak or a hazel tree or a lime tree does that. In broadleaf trees do that a lot. They have lots of little buds at the bottom, and yew is one of the only conifers to do that. So if the top gets broken, they can still sprout again from the bottom. And yew is an understory tree, so it wants to live for a long time, so it can grow underneath the canopy of another tree. If it gets chopped down, then it can produce new shoots on the outside. And so what you find is that some of these incredibly old yew trees, which you find in churchyards, the centre, the main part of the tree is long since died, and the outer parts are actually new bits of the tree which have grown later, and the whole thing can survive, therefore getting wider and wider for hundreds and maybe thousands of years, and it's all down. So it's down to that capability and the fact it is designed to be a tree growing in the understory of other trees and to live a long time. Has lots of defense chemicals in it. It's very dark wood, and that's how it manages to survive for that length of time.
Thank you. Right, you mentioned tannins. Can
Yeah.
you tell us a little more about them, as they can be destructive to other materials such as lead?
The short answer to that is I don't know much about tannins at all, I'm afraid. Not really. I'm afraid my brother, who has worked on tannins as defense chemicals of trees, would be able to tell you more about this, but unfortunately I don't know anything about really much about that, I'm afraid. I'm sorry.
That's okay. That's we can't know everything. Right, so next one is on the topic of diseases. How does somewhere like Stourhead, with so many non-native species, live in the equilibrium? And is there a mechanism that trees use to coexist, i.e. to collaborate in an environment?
Well, the tree, as you said, the lovely place Stourhead, there are loads of different exotic trees growing in Stourhead. As long as a tree is adapted to a similar climate, then it won't have any problem living in Britain at all, as people have found. And indeed, it might have the advantage of growing here in that it's left a lot of its pests and diseases behind it, and there aren't any pests to kill it in this country. So that's one reason why exotic plants often do better in a new country. There's some good evidence that trees do can help sort of limited extent help each other. There's an awful lot of talk about how trees cooperate together nowadays, the so-called wood wide web, where they're linked by networks of fungi, mycorrhizal fungi under the soil, and people are suggesting that the trees are all helping each other, and the fungi are acting just allowing that to happen. I don't think that's actually very likely myself. I think that's just a story that people like to hear because it sounds good, and it sells lots of books. But the reason not is that the fungi are there for themselves, and so it may well be that the fungi underground they might move sugars and things around to help themselves, and then you might think that the underground fungi are like sort of tree farmers, and that by looking after the trees above them, they're improving their own chances of survival. So that's looking at it. You could look at the world from a fungi-centered one rather than a tree-centered one. You get quite a different impression. It's a complicated world. All these interactions are incredibly complicated, but I don't think we should just look at a simplistic idea of trees being nice to each other. It just doesn't work from a sort of evolutionary point of view.
Okay, well, I've heard that story. It does sound interesting, but perhaps bursting the bubble now. but something's happening down there.
Yeah, it's a sort of story that people want to believe, so people will believe it, even though there isn't much evidence yet. There's something interesting happening, but that's just one interpretation that people have put on a few facts. And there's, as I've just mentioned, you can have an entirely different interpretation, quite different, but
well, sounds like it's inspiring enough to get people to research.
Yeah, well,
that's the main point, isn't it?
Yes, that's true. Yes.
That's what I want to know more about.
Yeah.
Right, I do have another question. Is it a fungus that causes the colour change in the heartwood of ash to create olive ash and brown oak?
I think the answer is probably yes. I don't know too much about that, but there are all sorts of a lot of the different fungi do cause different trees to go different colors, and there are enormous numbers of different fungi you can get, which attack different parts of the materials within the wood of a tree. So, for instance, you get brown rots, white rots, soft rots, and some of them attack the cellulose, some of them attack hemicellulose, some of them attack lignin, some of them attack pectin, and they have different effects on how the wood breaks up and how the tree dies, and they also can cause fantastically beautiful different colors within the wood. So yeah, that's another entirely fascinating subject that about which I know very little, sadly.
Well, it sounds like the research can just go on and on and on.
Mm.
We have a final question.
Right.
What are the advantages and disadvantages of working wood when it is seasoned?
Right. Yes. Well, it's the advantage of working wood when it's seasoned is that it's already undergone any shape change that it could undergo, because you're using it and you're shaping it in a room, for instance. It's dried out to room dryness, and therefore you can shape it, you can cut it, and you can form it and make beautiful shapes, and you make beautiful joints, and they won't change after that unless you put it into a room which becomes very dry or very wet. The downside, and that means you can do all sorts of fine carpentry and make incredibly beautiful things. The downside is that it's much more hard. It's much harder at that stage, stiffer, more difficult to shape, which is why early people tended to shape green wood. So, for instance, things like Windsor chairs can still be made when they're from green wood, easier to do, and you can do it in the open air, and then the whole thing dries out. The danger is with doing things in green wood, when it dries out, it shrinks. That could strengthen the joints, but on the other hand, it could also split the wood and cause damage later on when the whole thing dries out. So it's a question of precision versus ease of shaping.
Well, thank you. And that's all we have time for tonight. Thank you ever so much for your wonderful presentation and good answering of the questions. And thank you to all for watching and participating tonight. I hope you enjoyed the talk. When the Zoom screen closes, a short feedback survey will pop up, and we'd really appreciate it if you could take a few minutes just to fill that in, because we use all of that to help guide future talks that we do. I'd also like to take this opportunity to invite non-members to join the consortium, either as a supporter or practitioner, and all details are on the website. And the other thing that all details are on the website are for our next talk. And the next talk will be the second in the series on wood on the 8th of November. Its topic is why preserve archaeological wooden remains. And through a series of case studies ranging from the Mesolithic to the 1960s, this webinar will consider the reasons why waterlogged archaeological wooden remains are being preserved. So go to the website for more information and do log in and register. So thanks to everyone, panelists and those for you watching, and it's just a good part of saying good night.
Bye-bye.
Goodbye, Roland.
Bye-bye.